Alright, here I have the SAT chemistry practice test from Crack SAT. And what I plan to do is go through a page of these a day and create a playlist for each of the different units. So this one is phases right here. So how I'm going to do this is I'm going to look at the type of questions they give you. So in question type A, right here, you're given 3 statements, and then you have to match which of the following. So if you see that you have 3 questions here and 5 options up here, so some of them aren't going to be used. And the second question is like asking if the first statement's true, if the second statement is true individually, and then asking if statement 1 is true, is it true because of statement number 2? So I know they have the answers on here online, but I do find it helps if you have somebody kind of talking you through it instead of just reading it. So for the first question, number 10, it says it's inversely proportional with moles of a gas. So that means when something goes up, the other one goes down. That means inversely proportional. So when other variables are held constant. Okay, so that automatically crosses off the first option for number 10 because the ideal gas constant, it has it in its name. It's going to be constant. So it doesn't have anything to do with the moles of a gas increasing or decreasing. Celsius temperature doesn't have a we don't use that in our ideal gas formula. We use Kelvin because Kelvin does have a representation of absolute zero, which would be 0 Kelvin. Celsius is just like the representation that we use of something being like hot or cold. Kelvin's the measure of the kinetic energy, so it's not going to be the Celsius temperature. I'll go to the bottom with volume because we know we have a formula with volume in number of moles. So if you have a deflated balloon like this, and then you blow into it, it gets a lot larger. So if you increase the number of moles, then that means the volume is going to increase. So that would mean that they're directly proportional. So we know it's not going to be volume. And then partial pressure doesn't really have a ton to do with it. There's a better option here, and that's C. Now why it would be Kelvin temperature is because it is the temperature that we use in the ideal gas formula. And because, let's think about this, if we write out nRT, PV equals nRT. Let's say that these two values are just 1 and 1. The number of moles, we'll say all of these are 1. So we'll have 1 equals 1. Now, it's inversely proportional to number of moles of a gas when other variables are held constant. So what that means is, I'm going to move this. So what that's saying is that if we still have 1 for our pressure, 1 for our volume. Now let's try this. We're going to put Kelvin temperature. We'll say we double that. And let's say that we do half the number of moles. So we'll keep the R the same, and we'll say half. Are we still going to get 1 equals 1? Yeah, we will. So that means that these two, the number of moles and temperature, are inversely proportional. So if one goes up, the other one goes down, and you'll still keep this 1 equals 1. So let's try another one. Let's see if we do it as in like they're directly proportional, meaning that if you increase one, then the other one will increase. So we'll have pressure and volume equal to 1. Number of moles, we'll say 2. Temperature, we'll say 2. Well, then we have 1 equals 4. So you know that they can't be directly proportional. So they're on the same side. So that must mean that they're inversely proportional. because they're on the same side. Okay, so that would be C. Okay, sum of each gas in the mixture yields a total for that mixture. So let me erase these. Well, in the beginning I went over what these terms mean. So the sum of each gas in the mixture yields a total. So when we look at the total pressure equals pressure of 1 plus pressure of 2 plus pressure of 3 and so on. What that is saying is that's our partial pressure. So if we add up all the partial pressures, then we get the total pressure. And it's the average kinetic energy of the gas molecules in a closed container using the ideal gas equation. Well, then I just said that earlier that we know that that's going to be C. So with those three, like I said earlier, you have 5 different options here. You see, we didn't use volume, we didn't use Celsius, and we didn't use the ideal gas constant. Okay, so for number 9, we're going to see, we first want to say, is this true or false? If each of these individually are true or false. If an ideal gas is located in a closed container and the temperature is increased, the average speed of the molecules will increase as well. Okay, so that should make sense. If you increase the temperature of something, you're adding energy to the closed system, which therefore will increase the speed, the speed of the molecules. Okay, so we know that that first one's true. Now, the second one, is it true or false? For an ideal gas, temperature and moles are inversely proportional. So, for an ideal gas, temperature and moles of a gas are increasing or are inversely proportional. Okay, so let's look back at this original. Well, let's write out the PV equals nRT. So inversely proportional. Remember, if the two variables on the same side, that means inversely proportional. Now, if they're on different sides, then that would mean directly proportional. If everything else is held constant. Okay, so if, let's say, again, I'll write out another example of that, just how we did in the first part of the question. So we have, this is 1 and this is 2. Okay, so if we have 1 equals 1 equals 1. So temperature and moles are inversely proportional. So if we do 1 equals 1/2, so we half the number of moles, keep R constant, and double the temperature. We still get 1 equals 1. Okay, so that means that they're inversely proportional. So if you cut in half the number of moles and you double the temperature, then it will be the same. Okay, so this is also true. Now, what they're asking for that third part is, or are they both true because of something? So if it reads out, if an ideal gas is located in a closed container and the temperature is increased, the average speed of the molecules will increase as well. Because for an ideal gas, temperature and moles of a gas are inversely proportional. Okay, so let's ask if that makes sense. Okay, would it make sense for the temperature to increase because the moles were cut in half? Okay, so if we have let's draw a picture of it. So let's say we have a balloon filled up, and let's say we let some of the air out, and it gets smaller. Is that because, oh no, sorry. So we have the balloon, and this is the same balloon. So if we let the air out of this balloon, will the, see, it doesn't make sense in my head, so it's hard to give an example. So the temperature in here, let's say this is 298 Kelvin, and let's say that this one is 300 Kelvin, or 300, I'll do 320. Okay, so we had an increase in temperature. Was that because of us letting out air? No. So even if both of these statements are true, it's not because of each other. All right, so we can have two true statements here, but just because they're both true doesn't mean that it's because of both the statements. Okay, so those are the type of questions that are going to be that I'm going to be going over. So this would be part 1 of probably 7 or 8.